Hello, my name is Ryan Seelig. I'm a PhD student from UNSW Sydney, and today I'm going to be talking about going from Vaughan Jones connections to new infinite simple groups. And this is a joint work with my PhD supervisor, Arnaud Brothier. So here are the two main characters of the talk today. On the left, we've got Fields medalist from New Zealand, Vaughan Jones. And Jones was famous for finding deep and unexpected connections between seemingly disconnected areas of mathematics, like operator algebras and knot theory. About 10 years ago, Jones was working on some connections between conformal field theory, so physics, and subfactors, so more analytical kind of object. And during this work, he unexpectedly came across these famous groups from geometric group theory, Richard Thompson's groups. And so, inspired by this work and these unexpected connections, Arnaud Brothier um, constructed a new class of infinite discrete groups that are inspired by Jones connections and sort of Richard Thompson's groups. So what are Thompson's groups? Well, one way to define them is as groups of piecewise affine bijections of the unit interval, whose breakpoints, so where the slope changes, occurs at dyadic rationals, so those are numbers of the form a on 2 to the n, and whose slopes are powers of 2. So there are three versions. There's ft and v, and f acts by homeomorphisms on the interval. T, we can have some discontinuities, but if you wrap up the interval, you get a homeomorphism on the circle. And V, we naturally get homeomorphisms of the Cantor space. So those conditions I mentioned afford us a really nice combinatorial description of these bijections because these are really specified by two kind of partitions of the unit interval, which are defined by subsequently just cutting subintervals in half. That's encoded by a binary tree. And since we have two partitions, we get two binary trees with the same number of leaves. So if you want a homeomorphism of the circle, we kind of introduce some cyclic permutation between the leaves, which tells us which subinterval to send where. And it's cyclic so that we get a homeomorphism of the circle. So our main focus is going to be on the sort of circle type groups today. Okay. So Thompson's groups, they were famous for giving the very first examples of finitely presented infinite simple groups. And they come about in 1965. Okay. So what was Arnaud Brothier's idea? Forest-skein groups. They mix tree pair diagrams that we've seen just before with Jones planar algebra. I'm not going to be super precise with this today, but what it amounts to is taking multiple kind of abstract bifurcation kind of operations that we index usually by colors, so we call it a color set, and then we add in certain relations between these colored trees that we call skein relations. So here's one such example. So this is saying you basically take all binary forests with two colors, mod out by this pattern. Whenever we see this pattern, we can change it and vice versa. And note, it's important that we don't color the leaves of our trees. So we look now at sort of tree pair diagrams that we can form from this. And as I've mentioned, because we see this pattern here appearing in the skein relation, we can change it and we declare it to be the same. Okay, so just writing down any sort of set of relations is not always going to give you a group of tree pair diagrams in the sense that we want. However, if you just take one skein relation given by one blue colored tree, setting that equal to one red colored tree, this always satisfies the requirements we need to get some groups in the sense that we want. And so this is great because it gives us a massive plethora of very explicit new groups. And they're always going to be non-trivial in this setting and satisfy similar properties to Thompson's groups, but surprisingly some different things as well. So that's the kind of game. From this big class of examples, write down one in particular and then study what sort of things they satisfy. So for the rest of the talk, we're going to be concerned with this shape of skein relation. So this shape is very special and it's going to give us some really interesting new properties that haven't been seen before. And we're interested in the T-type one, so a group kind of acting on the circle. So some motivating questions for us. Do we get finitely presented simple groups? Just like how T, Thompson's group T, was finitely presented simple, is the circle version of the group we get here of tree pair diagrams going to be simple as well and finitely presented? And then do they have any new properties? So for simplicity, we have an attack. We can write down an action on the circle of this group that we call G. So that is of tree pair diagrams with cyclic permutations, and they're also colored. It's very similar to the one for Thompson's group. And we're actually able to deduce that the derived subgroup, so the commutator subgroup of this group, is simple if that action is faithful, just by classical arguments of Higman and Epstein. So we were able to show for this particular example that that action is faithful. And that's a non-trivial thing to do in our formalism. So we get a simple derived subgroup. Moreover, the abelianization of G, so G mod out by D of G, is finite. We can show this. And so that means that D of G is finitely presented. So we've answered this first question in the positive, which is great. Now we want to see if we get anything like new. So just to show you what a bit this action we construct looks like, to show you it's a little bit different, this is one element acting on S in this group action that I haven't shown you, but that we can construct. So it's kind of piecewise affine, but usually we only allow for finitely many changes in slope. This here has infinitely many changes in slope, and they're all kind of accumulating towards 1. So one natural question we can ask, well, is this somehow secretly just finite piecewise affine? And the answer we're going to see is actually no. So what do I mean precisely by piecewise defined homeomorphisms? Well, we've seen piecewise affine or piecewise linear, where you are acting affinely, except for at finitely many points. And we call this group of all piecewise affine homeomorphisms on the circle PL plus S. Plus is for orientation preserving. There's also a weakening of this called being piecewise projective, and that's now on these subintervals we can act by fractional linear transforms. And there's a way in we can talk about the piecewise projective homeomorphisms on the circle. And so what's interesting is that just about all finitely presented simple groups in the literature that act on the circle by homeomorphisms, they all do so in a piecewise linear way, except for one example found in 2019 by Loader, which is piecewise projective, but Loader was able to show that it admits no piecewise affine action. It was quite an interesting group of homeomorphisms. So we're interested, does the same thing happen for us? I mean, we had an action that was not quite piecewise affine, but does that mean that it cannot have any piecewise affine actions like this here at all, with only finitely many breakpoints? And as I mentioned, the answer is yes. So there is no piecewise affine actions for this group G that we defined a few slides ago, but in fact, something stronger. There's no piecewise projective actions either. So it's also not among Loader's construction as well. So here are the core ideas. A very famous theorem of Bryndon-Squire tells us that piecewise affine homeomorphisms, the group of piecewise affine homeomorphisms on the real line, can't contain any non-abelian free subgroups. And Monod was able to adapt this very nicely and show that piecewise projective homeomorphisms on R also satisfy this property. So then, using this in our minds, we're able to construct these certain embeddings of the non-abelian free group inside our derived subgroup D of G. And what this does then for us is obstruct being able to act piecewise affine or piecewise projective on the circle. Indeed, if you took any piecewise projective action on the circle of our group, well then using some techniques from bounded cohomology theory, namely like Gis has a classical theorem that we use and some more recent things of Fournier-Fascio and Loader, we're able to show that any such action here would induce an embedding of the non-abelian free group into the piecewise projective homomorphisms on R, which we know by the Brin-Squire theorem, gives us a contradiction. So that's it. We've found a new dynamical property among this new class of groups, and it's finally presented and it's simple. So thanks for listening to my talk. Here is the literature associated to what I've been talking about, so you can find more details in these papers. Thanks for listening.